Hello, everybody. Welcome to today's lecture. Today we're going to keep going with chapter 3. We didn't make it through 3.1 yesterday or last time. We got to the 3 different types of probabilities. So today we're going to continue on and start talking about complement probabilities and then some other probability rules that'll help us when we're calculating probabilities, because that's mostly what we're going to want to do. So we'll start today talking about complements, but let me first just give you a refresher of what we did last time. Let's just go to the top and summarize. One big thing was the sample space. Okay, so this is always like a good first step whenever we're tackling a probability problem, is think about what the sample space is. You don't necessarily always have to write out the entire sample space, but if you can, it's a good idea. But sometimes the sample space could be very large, so you might not want to. But the sample space is a set of all possible outcomes, right? So if you're drawing a card from a deck of cards, then it would be each of the 52 cards would be your sample space, right? Because those are all the possible things that you could draw. We call doing an experiment a trial. So like drawing the card would be called a trial. Here were some examples of sample spaces. And then an event is any subset of the sample space. So that's usually what we're looking for, is the probability that an event happens. So it could just be like the probability of drawing a 4, or it could be the probability of drawing a 4 or a 6 or a 10. And we'll talk about those kind of rules today. Maybe it's the probability of drawing a 4 and a red card. Okay, how do we deal with that? That's another thing we'll talk about today. And then if we have equally likely outcomes, which we basically always will, at least in our case, this is how we calculate the probability. This is read as the probability of A, whatever A is the number of ways for A to occur divided by the total number of outcomes. Okay. So we saw probability of getting a heads is 1/2 when we flip a coin. Probability of rolling a 5 is 1/6 if we roll a 6-sided die. What we're going to look at today, what we're going to start with, is a complement probability. So for example, with the probability of rolling a 5, we know it's 1/6. So what's the probability of not rolling a 5, right? And there's a few different ways we could think about that. So let's get started with the new stuff today with complement probabilities. Okay. Okay, so the complement of an event E, so this could be anything. This could be like the A we were using before, which is denoted by E bar. Okay. So E with a bar over it. So I'll write in parentheses E bar is the set of outcomes in the sample space that are not in the event E. So before we go on, there's a little bit more to the definition, but let's think about this part first. So the complement of an event E, which we denote by E bar, is the set of outcomes in the sample space that are not in the event E. Now, just some notation here. Okay, the book here uses E bar, but there's some other notation that's pretty common for this. Let me write. So this is the same thing as E with a C. It kind of looks like an exponent, a superscript C. Okay, it's usually a capital C, but sometimes it's a lowercase c also. So this is, the C is for complement. So this is E complement. You'll often see this used. I'll stick with E bar since that's what the book uses. But most things I've seen will use E complement. And sometimes you might also see E prime, which is like E with a little like dash on the superscript. Okay. That one's probably less common, but I have seen it used before. Okay. In fact, we might even end up using that for something else. So I'll just go ahead and get rid of that one. But just know that sometimes that is used. But E complement, EC, is used a lot. Because when you go further on in math, the E bar is usually used for something else. So we use this one for complement instead. That's really all there is to it. So what does it mean by this? Is the set of outcomes in the sample space that are not in the event E. So let's kind of try to visualize this, right? If we try to visualize this geometrically, okay, let's say this big space is S. So that's the sample space. Okay. So this is our space S. And then inside here, we have E, right? Maybe I'll write S inside here. So this whole big thing is S. I guess that's how we would write it, right? Like right in the middle. The whole big thing is S, the sample space. And we know E is a subset of that sample space. So it's going to be something inside of the sample space. It's part of it. So if that's E, let me get rid of this now. Then the whole part outside of the sample space, this part, the whole part outside of E is going to be E complement. Which, like I just said, I'll write as E bar. Okay. So if that is E, then the rest of it is E bar. If we think about the sample space as we did before, where we roll a die, then our sample space, 6-sided die. So our sample space is 1, 2, 3, 4, 5, 6. Okay. If E is 5, okay, so this would be like we did before, the probability of rolling a 5, then E bar is everything except for 5. Okay. So 1, 2, 3, 4, and 6. So we already established before that the probability of E was 1/6. So now the question is, okay, what's the probability of the complement of E? So in other words, in words, this would be what's the probability of not rolling a 5. And so what we do is we count how many different ways can that happen. In other words, how many different parts are there in E complement? And there's 1, 2, 3, 4, 5 different things that can happen. And we divide that by the total number of things in the sample space, which if you can see right here is 6. So the answer is 5/6. Okay. So one thing that will hold true for all of these complements is that the probability of E plus the probability of E complement is equal to 1. Okay. In other words, if you take the probability of getting some event and the probability of not getting that event, they should add up to 100%. Okay. Which should make sense because those are the only two possible things that can happen. You either the event either happens or it doesn't happen, right? So those are the only two possibilities. One of them has to happen. So they should add up to 100%. So when you're talking about flipping a coin, you can think of you either get a heads or you don't get a heads, right? So the probability of getting a heads is 1/2. The probability of not getting a heads is the same thing as probability of getting a tails, which is also 1/2. And 1/2 plus 1/2 is 1. Okay. So this leads to the more useful formula. If we subtract the probability of E from both sides, which is that the probability of E complement is equal to 1 minus the probability of E. Okay. So if we know the probability of something, then we can easily find the probability of its complement by doing 1 minus that thing. And you could flip this the other way too if you wanted to. The probability of E is 1 minus the probability of E complement. Okay. But it doesn't really matter which of these you use because they're the same thing. You just might have to do more algebra if you do it one way. And this holds true with our, probability of not rolling a 5. So probability of not rolling a 5 should be 1 minus the probability of rolling a 5. Based on this formula right here. Okay, E complement is not rolling a 5. E is rolling a 5. So this is 1 minus 1/6 because we know that's what the probability of rolling a 5 was. And then you can do your fractions subtraction. So you do 6/6 minus 1/6, find the common denominator, and you get 5/6. Okay. Which is the same thing we got up here without the formula. Okay. So this can be very useful because oftentimes it's easier to talk about the probability of things not happening rather than the probability of things happening, which we'll see a context for that a little bit later. Okay. Let's just think about real quick, what is the probability of standard 52 cards in a deck? What's the probability of drawing a red 4? Okay. So we got to think about this. Okay, so the probability of drawing a red 4, this is like the problems we were doing last time. We know that there's 4 4s in the deck, right? There's 4 of any number in the deck. And there's going to be 2 red ones and 2 black ones. The 2 red ones are the diamonds and the hearts, and then the black ones are the clubs and the spades, because we talked about those 4 suits. So there's 2 different red 4s in the deck. There's the red of diamonds and the red of hearts. So there's 2 ways for this to happen, and there's 52 total cards in the deck. So it's 2/52, which you can simplify if you want to 1/26. So knowing that, now we can think about, okay, what's the probability of not drawing a 4? Okay. Well, we don't have to go through every combination of cards that, or sorry, this should be red 4. We don't need to go through every combination of every card that's not a red 4 and count them all. Instead, we can just do 1 minus 2/52 or 1/26. It doesn't matter. Let's use 1/26. So just using our formula right here, because this is the complement event, we can just use this formula and then we don't have to count the other combinations. Okay. So we get 1 minus 1/26. So we find a common denominator. 1 is the same thing as 26/26. So we get 25/26. If you're more comfortable with decimals, you can do this with decimals too. That's easier to do in a calculator. You just might have to round a little bit. All right, so let's go on to the next part now. Um, let's talk about impossible and certain events. Okay. So if the probability of A is equal to 0, then we say A is impossible. Okay. So this would mean that there is a 0% chance of A happening. Okay. Now, if you get into the technical details of this it can get a little fuzzy. Like, it doesn't necessarily mean that A will never ever happen. For example, one cool thing you can do if you think about all the numbers between 0 and 1, for example. So that's like all the fractions, all the decimals, like 0.3, 8, 2, 4, whatever. So you think of all the numbers between 0 and 1, and you think about, okay, what's the probability that if I picked a number at random, that the number would be 1/2? And what happens is that the probability is 0. And that's just because there's an infinite number of numbers there. So the probability that you pick any one of them ends up being 0, um, which is really strange to think about. Because obviously, if I asked somebody to pick a number between 0 and 1, it's probably very likely they would pick 1/2. Um, so it doesn't necessarily mean that that will never happen. It's just that if it was truly random, it would be impossible. Okay. Obviously, if I ask somebody to randomly pick a number, it's hard to actually do that randomly. We're biased towards the numbers that we use often, like 1/2. Um, so it can get a little fuzzy, but for our purposes, we're just going to think of it as impossible. Okay. On the other hand, if the probability of A is equal to 1, then A is certain. Okay. That means it's guaranteed to happen. The probability that it happens is 100%. Okay. Um, so probability of A being 0 typically means that it's outside of the sample space, and the probability of A being 1 means that A is the entire sample space. Okay. Um, so like if we think about our sample space as heads and tails with a coin flip, right? So we're flipping a coin here, and we say, what's the probability of getting heads or tails? Okay. Well, this is everything in the sample space, right? The probability of getting either one of these, well, that's like what the entire sample space is, right? Those are the only two possible options. So the probability that we get one of them is going to be 1. So then on the flip side, the probability of not getting heads or tails is 0. Okay, because that would be the complement probability. You would do 1 minus the probability of getting heads or tails, which is 1. 1 minus 1 is 0. So getting heads or tails, at least one of them, is a certain event. Not getting heads or tails is an impossible event, right? So you could think like flipping the coin and it landing on its side. Could it happen? Maybe. I don't know. But we still are calling it impossible, and we're still saying that there's a probability of 0 for that to happen. Okay. So let's think about now about something called a probability distribution. Okay. the world of probability basically functions on distributions. What this is, I'll write down the formal definition in a second, but it's essentially just a list of every possible thing that can happen. Or if it's not feasible to make a list because there's like infinity of them, some mathematical way of representing every possible thing that can happen. Okay. So let's write down the formal definition here. All right. So here, let me just use this here. A probability distribution, which is sometimes also called a probability space, is a sample space, hence the name probability space, paired with the probabilities for each outcome that should be one word in the space. Okay. So you just basically take the sample space and then you write down the probability of each outcome. So it's just a complete list of all of the possible probabilities, which can be helpful as a quick reference if you're working with the same sample space a lot. So let's just look at some examples. So it's just like a table. Okay. So we can have the outcome and its probability. The book writes it a little differently. It writes it horizontally, but I usually see it written vertically. Okay. So on the left side, we would have all the outcomes, aka our sample space. So, sorry, let's think about flipping a coin first. Okay. So we'd have heads and tails. Right. So these are the possible outcomes. And then on the right side, we write their probabilities. So we get 1/2, 1/2. And the total here, the total should always be 1. Because you're adding up all the possible things that can happen. So altogether, there should be an 100% probability. Okay. So it goes through some more of them. We really just need to know, you don't necessarily need to be concerned about how to make these tables as you do about how to read them. Because oftentimes a problem will give you a probability distribution table and you'll just be expected to get the information out of the table. Okay. So let's just think about rolling a die. Okay. So we have our outcome and our probability. Okay. So this is going to be 1, 2, 3, 4, 5, and 6. And this one's not too much harder than the last one because these all have the same probability, right? They all have a probability of 1/6. Okay. So this would be the probability distribution table for this. And you can confirm when you add up the probabilities, you get 6/6, which is 1. Okay. Let's think about the a little bit of a tougher problem. What about the probability distribution for the sum of 2 dice? 2 dice. Okay. So we roll 2 dice and we look for the sum. Okay. I think it's helpful to make a table with this problem. And then after that, we'll copy that. We'll use that table to look at the probability distribution. Okay. Let me see if I can do this a little more neatly. Okay, so we'll make a table. Yeah, we can just actually make a real table. So we have 2 dice. So along the top, we'll have 6 different numbers, right? And we'll leave a buffer on the first number. And then along the bottom, we'll have another 6 numbers. So we'll do it like this. Sorry, I don't know how the table function works in this. So let me just work on resizing this. Here, let me pause and I'll figure this out. All right, I got it resized here. So along the top, we'll write all the possible outcomes. Sorry, it's not working. Hang on again, one sec. All right, I got it figured out now. Sorry about that. So we'll write the outcomes for the first die along the top here. And then the outcomes for the second die along the leftmost column here. And then let's change the colors for the inside. Let's go with red. So then in this column, for example, we're going to write the sum of the first die and the second die. So we're going to have 2. Sorry, I'm having all kinds of problems with this right now. Give me one more second. Okay, let's try this one more time. So we'd have 2 right here. 3, 4, 5, 6, 7. Right, because we're just doing the sum of each of the 2 dice here. And then we'd have 3, 4, 5, 6, 7, 8. Sorry, this is so messy. My screen is messing up, so I can't see where exactly I'm writing it. So I just kind of have to eyeball it. Okay. And we got 5, 6, 7, 8. There we go. Now I can see it. 6, 7, 8, 9, 10, 11. And 7, 8, 9, 10, 11, 12. Okay. So we can see here there are 36 possible things that can happen. But there's not 36 different numbers, though, because some of them can happen multiple times. In fact, most of them. Like for 5, for example, there's 1, 2, 3, 4 different ways it can happen. So let's put this together in a table now. So let's go outcomes and probability. This one we're going to have to think about a little more. But we can see all the possible outcomes at least, right? We can see there's 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, sorry. I didn't notice that was so far down. 7, 8, 9, 10, 11, 12. Okay. Actually, you know what? It'd be a lot neater if I just made this into another table like this one. So let me do that. All right. I got this table made. So we have outcome and probabilities. So we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so we got all of our possibilities here. So let's think about what the probability of each one of these would be. So if we remember, the probability is the number of ways this could happen divided by the total possible outcomes, right? So we just go here and count how many. We know that there's 36 total possible outcomes. So how many different ways are there to get a 2, for example? So for 2, there's only one way to do it. It's just this first box here, right? You get a 1 and a 1. That's the only possible way you have a sum of 2. So our probability is going to be 1 over okay. Yeah, so 2 has a probability of 1 over 36. Okay. And then we go up and see, okay, how many ways are there to get 3? There's this box right here and this box right here. So there's 2 possible ways. So that's 2 out of a total of 36. So all the denominators here will be 36. The book gives it 2 different ways. It has like the reduced fraction also. So like 2 over 36, for example, would reduce down to 1 over 18. So you could write it that way if you like. For 4, there's 3 possible ways. So we get 3 out of 36. 5, there's 4 possible ways. So we get 4 out of 36. And then 6 will be 5 out of 36. 7 is where it peaks. There's 6 possible ways to get that. Okay, so 6 out of 36. And then it starts to decline again. For 8, there's only 5 ways. So then we have 4, 3, 2, and back to 1. Okay. And if you add all these numbers up, you'll get 36 over 36, which is 1. Okay. So this can be helpful if, if we had to answer a lot of questions about the sum of 2 dice, and we didn't want to calculate it by hand every single time. Like, if we think about 7, if we don't want to have to go through, find all the different combinations that would give us a sum of 7 and make sure we don't miss any, then it would be easier to just make a table of it. Okay, but like I said, most of the time you're not going to be asked to make these tables. Rather, you would just want to know how to read the tables. Okay. Okay, so that's a probability distribution. Last thing in this section that we want to talk about, I believe anyway, Yeah. 3.2 is when we'll start talking about the like combining events. So the last thing in this section is about odds. Okay, this is probably a very common way you've experienced probabilities, right? What are the odds that something happens? Great example here in Louisville. You know, you have the racetrack with the horse racing, with the like Kentucky Derby, right? There's always odds for all of the horses. So what do those odds mean? We typically think of them as like a betting context, right? And we know that um we often are given the odds, like maybe this horse is has like a 2-to-1 chance of winning or something like that, right? Um so we typically know like how much money we're going to make off of that, but what did those odds really mean? Where did those numbers come from? Okay. So um the odds, whoops. The odds for an event E, which we might write as O of E, O for odds, are given by the probability of E divided by the probability of E complement. Okay. Um So it's the probability that E happens divided by the probability that it does not happen. Okay. Um so what are the odds of rolling a 5, for example? Okay. If we were going to bet on the outcome of the dice roll, what would the odds be? Well, the probability of rolling a 5, which we'll call E, is 1 over 6. And thus the probability of E complement is 5 over 6. So our odds is 1 over 6 divided by 5 over 6. Okay. Now, if you remember from dividing fractions, okay, this is the same thing as 1 over 6 divided by 5 over 6. This is how we typically see it. You do the same change flip. You leave the first number the same, change the division to multiplication, flip the second fraction. Okay. 6's cancel out here, and we get 1 over 5. Okay. So the odds of rolling a 5 are, we would write 1 to 5, or 1:5, which is just another way of writing a fraction. Okay. So when you're talking about, you know, the odds of a horse winning are 2-to-1, we're saying the probability of them winning divided by the probability of them not winning is 2, essentially, because you'd have 2 divided by 1. So in other words, it's twice as likely that they win as they don't win. Okay. So maybe the probability of them winning is 2/3, and the probability of them losing is 1/3, or something like that. So I mean, we see this all the time with betting, right? And typically the greater the odds, like if you had like 72-to-1 odds, then if this is typically saying like it's typically stated this way a little bit backwards from how we're stating it here. It's like very unlikely that this is going to happen, but if it does happen, then you're going to win a lot of money. You're going to win $72 for every dollar that you put in, typically. Okay. So that's how we would read that. Let's just do like one more example for odds here. Let's say, what are the odds of getting a sum of 6 with 2 dice? Okay, so that probability distribution table we just used. And we'll call the event E again. So what's the probability of getting a 6? We already found it's 5 over 36, right? What's the probability of not getting a 6? It's going to be 1 minus this, right? So 1 minus 5 over 36 we can write. And then you got to simplify the bottom here. 1 minus 5 over 36, you would make it 36 over 36 minus 5 over 36, so you get 31 over 36. Okay. And then you do your same change flip. And you get 5 over 31. Okay. So the odds are 5 to 31. Not typical odds we would see. Usually when odds are reported, they're nice even numbers. Like for horse racing and like probability of winning games, and for example, they're usually giving you nice numbers like 72 to 1 or 2 to 1 or something like that, because they're not exact anyway, right? People are just estimating what the probability is based on their models. You can't know for certain what the probability of a horse winning is. It's just whatever the official, whoever makes the models, whatever their models are predicting, and they're going to round it a little bit to make the numbers nicer. So you're not going to see typically like 5 to 31, even though maybe that's what it really is. Okay. Maybe they would make it 5 to 30, which would simplify to 1 to 6 or something like that. Okay. So this is how we'd find it, though. We do the probability of it happening divided by the probability of it not happening. Okay. All right. We'll stop there for today. Next time we're going to start tackling 3.2, which is talking about the and the or rule. So this is like, what's the probability of rolling a 5 or a 3? Or what's the probability of drawing a 4 and a red card, which we kind of already thought about by rephrasing it as a probability of drawing a red 4. So we should get the same thing. So how do those rules work? And we'll talk about independent and mutually exclusive events, which are important for those rules. So yeah, I will see you guys then. Thank you for watching today.